Okay, so you're going to need to have access to a calculator if you would like. You can use your calculator on your phone, that's fine. For the test, for this particular reason, you will also have access to a calculator, whether you take it on Respondus or whether you take it in the testing center. You do need to take a look at those in-class questions for Chapter 2. We're going to be working through quite a few of those today. And I think that's about it. I don't think you need your periodic table for this one because I'm going to give you, like I am on the test, you're not going to need your periodic table. You're going to have access to snippets of the periodic table. So let's go ahead and get started. So looking at our levels of organization that we learned in Chapter 1, you remember you're going to need to put these in the correct order. As I said, the levels of organization kind of follow the textbook. So that's why, believe it or not, Chapter 2 is a chemistry chapter because we're building the human body from the atom up. And this particular part is starting with, let's talk about the atom. You've got this picture in your handout just to kind of show you the structure of what's going on here. And the reason why I wanted to show you this is because, yes, we've said that your protons and neutrons are located in the nucleus. The protons are the positively charged and the neutrons are the neutral particles, and they're located in the nucleus. Now, we also said that the electrons are located in the electron cloud. But what I didn't say is exactly how they're organized in the electron cloud. They're not just thrown in the electron cloud willy-nilly. They're actually organized in levels or orbits outside of the electron cloud. So this first orbit right here that's closest to the nucleus, this would be orbit number 1. This one right here, as you move outward from the nucleus, you just count to the next level. That'd be number 2. If there was another one, it would be number 3. Now these orbits, as you notice, the first orbit is smaller than the orbit number 2, and then orbit number 2 is going to be smaller than orbit number 3, and so on and so forth. So these orbits have a certain amount of electrons that they can hold. I am not asking you to memorize any of this, but I need you to understand some terminology that we're going to be getting into in a minute, and you need to understand what an orbit is. So orbit number 1 just happens to only be able to hold 2 electrons. It's just that small. It can't hold any more. I don't care what atom you're looking at. I realize that all atoms are different sizes, but it doesn't matter which one. The first orbit can only hold 2 electrons, period. The second orbit can hold a maximum of 8. Now, this one doesn't have 8 electrons in it, but it could hold up to 8. And then the third can hold up to 18. And that's as far as we're going to go. Again, I'm not going to ask you to remember that for the test, but I need you to understand that these orbits are organized around the nucleus. Again, these electrons are not just thrown in this cloud willy-nilly. There's some organization to how these electrons are in this electron cloud. So how to read a periodic table. Now you have your periodic table in your packet there. You're welcome to take a look at it. So all I did here was take a snippet of the periodic table, specifically the section on oxygen, and I'm just showing you what oxygen's box looks like. So what does all this information mean? Well, most of the time you'll have an element name represented on the periodic table, so you can definitely see that. Just above, wrong direction, just above the element name is the symbol for the element. Now, for oxygen, the symbol is just a capital letter O. So some periodic tables just have symbols. They don't actually have names because they figure you already know them. Ours, the one I gave you, has both. Now looking at that, let's take a look at protons. You can actually determine how many protons an element has by looking at the periodic table information. The proton number, also called the atomic number, is found above the symbol. So remember where the symbol is, it's the capital letter there. Look above that, the number above it is going to represent the proton number, also known as the atomic number, and for carbon that is 6. Big key right here, the proton number identifies the element. What does that mean? If you look on that periodic table that you have, do you see any other element on the periodic table that has 6 protons? No, you do not. So what that tells you is if I say the atom with 6 protons, we all know that's talking about carbon. And if I say carbon, you all know that that has 6 protons. There's no ifs, ands, or buts about it. They just go together. So the proton number, if you know the proton number, you know what element you're talking about. So it can't be carbon if it has anything but 6 protons. If it has 6 protons, no matter what else is going on, it has to be carbon. So question number 5 on your in-class questions, go ahead and take a look at that, and I will give you a second to answer that. Sorry, I'm writing with my mouse, so that's why the wording is so awful there. The penmanship is so horrible. Okay, the proton number for iron is 26. What number on the periodic table tells you how many protons an element has? Well, that would be the atomic number, which is above the symbol. And then number 3, okay, that was a trick question. What 2 elements on the periodic table have the same number of protons? None of them do. Because remember, the proton number identifies the element. So if you've got a certain element that has 26 protons, that's the only element on the periodic table that's going to have 26 protons, and it is iron. No other element on the periodic table can have 26 protons except iron. So you're not going to find another one on there that has 26 protons. Now let's take a look at the atomic mass. So the atomic mass is also something that you can obtain from by looking at the periodic table. The atomic mass, by definition, is the number located below the name of the element. So the atomic mass for iron is 56. Now, I know that it's 55.845, but we're not going to deal with all those decimal points. So we're just going to round that number to the nearest whole number. If you remember your rounding rules, you're looking at the number that comes after the decimal point, which in this case is an 8. If that number that comes after the decimal point is 5 or greater, you're going to round up. So this is an 8, which means you're going to round that 5 to a 6. That's why the mass is 56. The atomic mass is the sum of all of the protons and neutrons in an atom. Now, I'm just going to give you a little bit of background information because you may be wondering, well, if we said the mass of a proton is 1 and we said the relative mass of a neutron is 1, how the heck are we getting 55.845 as a mass of an atom when each of those are represented by 1? That must be those leftover electrons. No, it has nothing to do with the electrons. We're going to learn this in one of the upcoming objectives, that there's this thing called isotopes, so which are different varieties of elements. So iron, there's not just one kind of iron, there's a bunch of different kinds of iron, and this is the average of all the different kinds of irons out there. So that's why it's a decimal number. You don't have to know that, but that's why, if you were wondering why it's not a nice whole number when our protons and neutrons are nice whole numbers, that's why. This is actually an average mass of all the different kinds of iron that's out there. Neutrons. Neutrons, you cannot look at the periodic table. The number of neutrons is not directly on the periodic table. You have to do a little bit of math to come up with the neutrons. The neutrons is the sum of protons and, so let me say that again. The atomic mass is the sum of protons and neutrons. So if you know the mass and you know the protons, you can calculate the neutrons by doing a quick little subtraction, and this is where the calculator might come in handy. So let's just take a look at boron on the periodic table. So if we were to take a look at boron and calculate its neutrons, what you're going to do is you're going to take the mass number. So keep in mind, we're going to round that 10.81 to an 11. That 8 is going to tell us we're going to round that up 1. So that's where we got the 11 from. And we're going to take the atomic mass, which is 11, subtract it from the atomic number, or the proton number, which is 5, and that gives us how many neutrons that has. So remember, this mass number right here is the sum of all of the protons and neutrons. And if we know 5 of them are protons, then the rest must be neutrons. So question number 6, I'll give you a second to take a look at this on your periodic table and on your in-class questions. In case you didn't have the periodic table in front of you, I went ahead and put the periodic table blocks of information there. Okay, so for fluorine, you can tell by looking at the atomic number, it's got 9 protons, and to get the neutrons, you're going to subtract the mass, which is 18.998, that's going to round to 19. You're going to subtract the 19 from the 9, and that's where you get the 10 from. For potassium, the atomic number, or the number of protons, is 19. You're going to take the mass number after you round it, which is going to be rounded to 39. And subtract off the proton number of 19, and that's going to give you 20 for the neutrons. So now let's take a look at the electrons. How do you come up with the electrons by looking on the periodic table? Well, keep in mind that electrons are negatively charged. They're represented by those negative green circles there. Protons are the positively charged particles. They're blue, and notice they're located inside the nucleus. If you remember that bullet point for the characteristic of an atom that we talked about in a previous objective, we know that atoms are neutral, which means they have to have the same number of positive charges as they have negative charges, which means they have the same number of electrons as they have protons. So if you know the proton number of an atom, key word, we're dealing with atoms here, if you know how many protons an atom has, then it will have an equal number of electrons. So let's take a look at question number 7, magnesium and zinc, and go ahead and calculate the protons, neutrons, and electrons for magnesium and zinc. Okay, so hopefully you all got the same information I did. Again, keep in mind the reason why we have 12 electrons for magnesium is because we have 12 positively charged protons, and those need to be equal. If you take a look at zinc, we've got 30 positively charged protons. Therefore, we have to have 30 negatively charged electrons. So that number has to be the same because we're dealing with an atom. And then you can see the math there on how we calculated the neutrons. We just took the mass number and subtracted it from the proton number to get the neutron number. Okay, and I know you're like, wait a minute, we're doing this again? Yes, we're going to take a look at sodium a little bit more involved, so we're going to kind of do this one and then put this on the back burner for a minute. So go ahead and calculate real quick protons, neutrons, and electrons for sodium, because we're going to do a little bit more with sodium than we did with the other ones. Okay, so you should have gotten 11 protons, 12 neutrons, and then 11 electrons because your protons and electrons have to be the same in an atom. They have to be neutral. So your positively charged protons will equal your negatively charged electrons. And then I thought we could use a little bit of a break before we go on to the next section. Okay. Looking at the atomic structure for the sodium atom, I am not going to ask you to memorize this, but I do need you to understand a definition. So I need to show you what we're talking about here. Now, you can see in the nucleus, you can see your 11 protons and your 12 neutrons that are located in the nucleus. You can also see the electrons, which are negatively charged, and they are located in the electron cloud. The electron cloud is made up of energy levels. You have got your first energy level, which is the one closest to the nucleus. You have your second energy level, which is going to be a little bit further out. And then the third energy level is, for sodium, there's actually going to be 3 energy levels. And we said, again, you don't have to memorize this, that first energy level is going to have 2 electrons. That second energy level can have up to 8. And in fact, it does have 8. 1, 2, 3, 4, 5, 6, 7, 8. And you can see the third energy level, which can hold up to 18, actually only has 1. So you can see this is how those electrons, those 11 electrons, are organized in the sodium atom, you know, what energy levels they're found in. Now, I'm not going to ask you to do that. I'm not going to ask you to tell me how many electrons in sodium are in the second energy level. I'm not going to ask that, but I need you to understand the definition of what a valence electron is. Now, a valence electron, by definition, is the electron that's located on the outermost ring or the outermost energy level of an atom. So you can see with sodium here, the third orbit or the third energy level has got 1 valence electron. It can hold more, but it only has 1. So the rest of these electrons, I'm not really going to worry about as far as the name goes. They're called core electrons, if you wanted to know. They're just the ones that aren't valence electrons. As far as what we need to know, valence electrons are the ones that have all the fun. So we're interested in how many valence electrons atoms have. Now, on the test, I will show you a structure similar to the structure for sodium and ask you to tell me how many valence electrons that element has by looking at a picture. That's how I'm going to ask that on the test. So you should be able to see that by looking at the picture, this particular element, sodium, has got 1 valence electron. Again, I'm not going to ask you to memorize it. I'm not going to ask you to look at the periodic table and figure it out. I'm going to give you a picture of the structure of the atom of a certain element and then ask you to tell me that, how many valence electrons it has. So you do need to know how many valence electrons all elements on the periodic table want. While sodium only has 1 valence electron, it actually wants 8. Everybody wants 8. That's its happiest. Does sodium have 8 valence electrons? No, it does not. So it's a little mad little sodium atom because while it's neutral, yes, it doesn't have 8 valence electrons. Put that on pause. We will come back to how sodium is going to handle being mad about not having the right number. Okay, take a look at chlorine for a second. Go ahead and calculate protons, neutrons, and electrons for chlorine real quick. This is question number 10 of your in-class questions. I know if you've been in chemistry, this is probably going to drive you crazy, but chlorine, we're just going to go ahead and do our regular rounding rules here and say 35.4. I know that's 0.453, so we're going to go call it straight 35 for the mass. I know that's going to drive some of y'all crazy, but we're just going to leave it at 35 and keep our regular rounding rules. Protons for chlorine are 17, and we know that in an atom, the protons have to equal the electrons. So if you've got 17 positively charged protons, you will then have 17 negatively charged electrons. Do a little subtraction from the mass minus the proton number, and you have got 35 minus the proton number of 17 will give you 18 neutrons. Now, if we were to look at the structure of chlorine and see how those electrons are arranged in the electron cloud, we can see again that in that first orbit, we have got 2 electrons. We can see that in that second orbit, we have got 8 electrons, and we can see that in that third orbit, which is the outermost orbit, and that's going to determine, we're going to count the electrons in that orbit to determine the number of valence electrons. You can see that we have 2, 4, 6, 7. So chlorine has 7 valence electrons. Well, I actually just answered the question for you, didn't I? Because this is chlorine. So you can see that we have got 7 valence electrons. Now, the question is chlorine happy? No, chlorine is not, because in order for it to be happy, it would have to have 8 valence electrons, and it only has 7, so it's short 1. We're going to pause there on our unhappy sodium and our unhappy chlorine, and we're going to take a look at objective 5 next.